I'm sorry, but we don't have any more time for questions. We're going to move on to session number 4 regarding exposure to radio frequencies, and Mr. Olivier Merckel from Anses will be moderating this session.
Dernière session de cette journée extrêmement riche, donc consacrée à l'exposition. Alors l'exposition n'est pas...
This is a very exciting day. We're going to finish this. In fact, the conclusions are really a source of uncertainty on the effects of radio frequencies on health. In epidemiology, the uncertainty is clear. But this is also a way of acting on risk assessment. So we have to be able to correctly measure exposure to know what we're talking about. So I am going to ask Joseph Wout to come up for the first presentation on defining exposure to radio frequencies.
Challenges and changing in this domain. You see already different co-workers which are also part of what I'm going to present. So first, motivation. Why do we do measurements? Why do we do dosimetry? Already in the previous talks, and when I entered the building, I got a sheet of Stop 5G. So people are worried about these new technologies and need correct information. Also, there's in all European countries have their own legacies, so different norms. I'm from Belgium. Even in Belgium, we have 3 sub-countries, you could say, and 3 different norms in the Walloon, Brussels, and Flemish region. Also, IARC, WHO. They emphasized in the research agendas that wireless IoT, but also 5G needs to be investigated. And you see that in, in 2020, ICNIRP changed its norms. IEEE already in 2019, at the end of 2019, accounting for this 5G. And there is even funding, thanks to Anses, there is yearly a call. There's also now funding for European projects in Horizon Europe. So also Europe emphasizes on that this domain needs to be researched. So this is that was the motivation. This is the outline of my presentation. I'm first going to say some comparison. This was asked to me of 4G or legacy technology exposure and versus 5G. And then I'm going to explain 3 methods to assess fields in situ. This means in reality, in real environments. And then I'm going to apply one of these methods to 2 cases on big 5G macro cells, but also on 5G small cells. Okay, so we have the 5th generation of communication, and you will hear me saying sometimes more technical terms. And one of these is massive MIMO, massive multiple input outputs. This is one of the possible solutions to have these huge data rates, which I will explain for 5G. The picture of some arts, a colleague of me, is maybe most clear. You have a base station with lots of antenna elements, and because you have all these elements, you can steer a beam towards the user device. Another solution to have these huge data rates is the use of small cells. I come to that, but you can see here a smaller base station closer to the user, also generating communication and enabling these high throughputs. And now the question is, what is this impact? What is the uncertainty due to these new technologies? So I'm going to try to explain you the difference in exposure of 4G versus 5G, and then explain these different methods and apply them on small cells and macro cells. And I'll also for the first time try to explain some differences between users and non-users. So first, the cellular network evolution. This is a slide you probably have seen in the past, but you see here the evolution of 1G to 5G. In 2010, we did the first 4G measurements. It was in December. I know I did myself, minus 14 degrees in Stockholm, really cold in the snow. The first 4G measurements, then the promise was to have there 100 megabits per second. Now we're 2022 and we have 5G and we have promises of up to 10 gigabits per second. On the right of this slide, you see the commercial slide of 5G, or what it would promise to, with this 10 gigabits per second. You would have enhanced mobile broadband, massive machine type communications, and ultra reliable low latency communications. This is what 5G promises compared to 4G and the legacy technologies. So when I say legacy technologies, I mean the older technologies, 2, 3, 4G. So this 5G, how is this realized? By this massive MIMO that I mentioned, and then the picture of my previous slide, the small cells. But there's also a third solution. This is the millimeter waves. This is not being rolled out yet in most European countries, like in Belgium, the Netherlands. It's not in France. Maybe there are some test sites, but this is more in the US. You use a much higher frequency, like 28 gigahertz, then you have higher bandwidths, and then you can also, just like the massive MIMO or small cells, try to generate these huge data rates, low latencies of less than a millisecond, or these huge data rates. So this massive MIMO, explained this again here, you have more antennas than you have users, and in this way you can play with the amplitudes and phases and steer beams or create hotspots towards a user device. So what are these small cells? You probably know the macro cells. These are the big antennas you see in the city, and your mobile phone is communicating with these. You can go a step smaller, and these are then picocells. In Paris, there are several, hundreds probably of these. These are smaller cells serving less people than macro cells. Also in the airport, for instance, you have picocells. But you can go even a step much smaller, small cells, where you have, in fact, more infrastructure than you have users. For instance, you could say, in this room, you could have 2, 3 small cells, or 4, or even more, that you have small base stations, like Wi-Fi access points, but for 5G, closer to the user, being possible to have this high data rate communications. Another solution, and this is what is being rolled out, and what the main discussion in Europe is about, is in the 3.5 gigahertz band, the use of this massive MIMO. And I always like to use this figure to explain the difference. On the left, you see here 4G. This is how a classical base station works. We have a base station with a sector, 120 degrees. And in this sector, you have different user devices. And whether they communicate or not communicate, there's radiation everywhere. And the device can, if it makes a connection, can communicate with the base station. The difference, thanks to this massive MIMO for 5G, you have adaptive antenna systems, or massive MIMO, is that you have such a system with lots of antennas that you can steer a beam to each active user. So you see the pattern is completely different. Instead of this whole zone where everybody's exposed, you will have more beams towards the devices that are active. So to say this in words, 4G exposure will depend on the direction opposite with respect to the antenna. This is called the radiation pattern, the gain of the radiation pattern. Also the distance, of course, but also the global traffic. While for 5G, in fact, the active user is the one he or she is being exposed, in theory. Of course, in practice, these beams are not pencil beams. They have a certain width. For instance, at certain distances could be 10 meters wide, and it's possible to expose also nearby users. But to explain the difference, is that in the past, or what was present up to last year, was this 4G. Now we'll have exposure which will be dependent on the active user, really important active user, and also what he or she is doing. Whether he or she is streaming a video, having a voice call, or have maximum throughput by downloading a huge data file will cause different exposure. And we want to assess this exposure. We want to measure this. And for this, I present you 3 possible measurement methods. The first one is the one that governments, like in France, it's AMPERE, uses to check compliance with base stations, whether they satisfy the regional or national norms. This is called spot spectral measurements. So as the name it says, it makes use of a spectrum analyzer. You see this on the left here. This is our own spectrum analyzer. There are other types also. These are devices connected to a measurement probe, and the radiation is measured. A device that a lot of governments also possess, and V2 is the NARDA device. There's much more pre-programmed, also connected to a measurement probe, and you can also perform measurements. Less degrees of freedom, but these work also very well. Often these devices are combined with broadband probes to search the maximum. But what will be now the difference with 5G? Before 5G, we could just use a setup like you see on the pictures, do the measurement, and then report to the government, this is the exposure. For 5G, as I told you, we need an active device, then you attract the beam. So this will be novel for a government to do a compliance measurement. The government will not only have its spectrum analyzer, but also its 5G.
Donc c'est aussi le cas pour les appareils 5G qui attirent certains faisceaux. Donc la mesure de ces faisceaux
to check compliance with maximum possible downlink traffic. So what we do in practice, I will show you some results, is then 100 gigabyte file. So the whole base station is radiating towards this device, and then we can measure with the measurement probe the exposure of this. I need to define two quantities. When we do these procedures, we measure the maximum. I'm not going to go in detail, but when you do measure some technical parameter, the synchronization block, you measure the resource element of that, then you can do an extrapolation to worst case. So just remember, we measure maximum fields, but we measure also instantaneous fields, what is present at the moment where you do the measurements. So we have these two measurement quantities which are needed, average and the maximum fields. And then we design the measurement setup, which is part of an IEC standard. So first we do spectral measurement, then we do an in-band measurement. We do the measurement of the resource element and do the extrapolation, the average field, and we can compare with the international ICNIR norms, for instance, IEEE norms, or the regional or national norms, France, Belgium, and so on. You see the paper at the bottom. This is the first method. A second method is also interesting, is to have a monitoring network. So the idea is here to place some nodes. For instance, you see here such a small box on facades of buildings, on top of buildings, on lampposts in the city. And then you monitor continuously the radiation. You can also place them on vans to have mobile measurements. And what I show you here is an example in the city of Antwerp in Flanders, where we had here in a small zone, a smart zone, 11 of these nodes. We can create spatial maps, but what is also really interesting is that because it's a fixed network, you can monitoring during time. And that you see here a day-night pattern. During the night we sleep and have there's less radiation than during the day. We want these nodes to be low costs, and we designed ourselves, and this is one of our 5G measurement nodes, AMF sensors. You see the 5G band is included, but also 800, 900, and 1800 megahertz. This is quite sensitive and still has low costs compared to the spectrum analyzer setup, so you can place multiple in the city. By the way, in Paris there is also a network. Professor Wiart has also done research on this, and this is also part of Paris. I know also, for instance, in the next project, Smart Santander had also such a network. So, but what is interesting is that you clearly can see from such a node, again, day-night pattern, week pattern, so you see each time the days, or even over several years, so 11 nodes, and you see an evolution over time. You can look then, is radiation increasing over time? Is there, even with COVID, we could see the changes in behavior, more at home, more Wi-Fi usage, and so on. A third possible measurement method are the personal exposimeter measurements. with this is, you see some pictures here. These are kind of small boxes you can wear on your belt, in a backpack, and you can carry around. And you can carry around all day, and then you know your exposure during traffic, during commuting, I mean, during at home, at the office. And then you have really your personal exposure, personal dose. Professor Martin Reusley developed a protocol for microenvironmental measurements for this. This is always also used in survey studies. Sounds very good, but there is one big difficulty with these types of measurements. It's the results depend on the place of the body where you wear them. This picture nicely shows this. Assume you have a field here from the left, and we have the exposimeter here. Then you will have this yellow zone, so scattered fields. But at the other side, it would have been absorbed really a lot, and you will measure much lower fields. There are techniques to avoid this by having multiple nodes. And there is going to be a presentation of Marloes also about this. But these types of measurements are less suitable for compliance testing, but they're really suitable to see what happens in our everyday life. So I start again in 2010 here, where we compared these types of measurements in different countries. You see outdoor mobile telecommunications were dominating, uplink and downlink. But in the train, then it's our own device. Uplink, there was also a question this morning, from a mobile device towards the base station. So it's our own mobile devices which cause the highest exposure, for instance, in trains. But now we're 2022 and the 5G is there, so new devices have come on the markets. And also we designed a new protocol for this, which will have to be used. It's not only anymore environmental exposure, but also auto-induced. With that, I mean, again, a 5G device will be needed to be carried with a certain traffic in reality. So these studies become also more complicated because of the 5G, because an active user has different exposure than just somebody who is not using. So I apply now this first measurement method first on macro cells. And for this, I use a study we did in 2020, or we did a study in 2020 and 2021, but the measurements in 2020 in Switzerland, because there was a 5G network present. I have to say these were really low powers at that time because of the really strict Swiss limits. But there was a user device, and we could attract the beam of the base stations. So we measured not only the 5G, I put this in dark and bold, but also other telecom signals. And as you see in this picture, the 800 megahertz, 900 megahertz, but here is the 5G at 3.5 gigahertz. And now I compare two types of measurements. First, without the user device, so like the old way, you could say. And you see here a picture of the electric fields, a volt per meter for different positions. You see the field values, but in the color scale, you see the different technologies. Here is no induced traffic. I mean, we didn't use a 5G user device here. So we just measure what is present. And what you see here is this, there is almost no dark red visible here on this, in this figure. You see it also in the table, the dominating signals are the 800 and the 900 megahertz. The 5G without user device is really low and neglectable. But the picture changes when we have maximum downlink. So we download with a mobile device, 100 gigabyte file, maximum traffic of this base station, and then you see this dark red appearing on these figures. So then we have a contribution of the 5G. So this shows again that a 5G user device is needed in these measurement procedures. And you have similar values as, for instance, 2100 megahertz. Also, the cumulative value increases. Of course, the total impact of this was quite limited, really strict limits and initial starting network. Probably we were almost the only users in this network. In practice, of course, and during the years, more and more people will have 5G-enabled phones, there will be more traffic, and there will be different exposure pattern. What we also did is rescale these measurements to worst-case maximum powers, because this was not realistic. And here I show a cumulative distribution function of the electric fields. This is without a user device, so much lower than with the user device extrapolated and actually measured. Where you see if you do real measurements, you have lower values than the theoretical extrapolation, because in practice you cannot generate this theoretical maximum. You can try to approach it, but it's not the really maximum. And then typical values you maximally could obtain are here listed, about 5 volts per meter. This is about 0.6% of the ICNIRP norms. Okay. This slide puts it in perspective with other measurements we did. You see all the other telecommunication signals from in the past measurements, and then the 5G with without user device and with the user device is at the lower end. Okay, to conclude, I will just apply the same methods on 5G small cells. The interesting thing is these small cells are small in the sense they're only 5 meters high, serve a limited number of users, but we compare now an adaptive antenna system. So here is this with massive MIMO in the 3.5 gigahertz band versus an antenna system which has no massive MIMO. So like classical, it's 5G, but a classical microcell antenna. We rescale everything to small cell power, so the E100 classification and also maximum certain power of the adaptive antenna systems. And as I said, we will look at realistic use cases, somebody using a video call, and also at non-users which are alone in the network, and non-users which are next to other users which are active. And for that, we need to apply also a spatial temporal duty cycle, saying how much other users contribute to the exposure for the non-user. There's a paper of Torres about this with a factor 6 dB. We have also a paper of Sergei Shikantsov, and here we use about 5.8 dB, so similar number. These are the values. Just want to say electric fields as function of distance. We look also quite close to this small cell. So, and in red you see the first site with adaptive antenna system, and in green the microcell without the beam forming. But where I want to come to is this slide, where you have here first again the maximum fields. This is quite close to the base station. The numbers are not so important. It's a difference which is important. This is at 1.5 meters of this base station. People will normally not come that close. But the maximum here, you have here in one side the order of 13 volts per meter, and here 36 volts per meter. If you have then a real user with a video call, this reduces to 4.2 to 15 volts per meter. You see quite a reduction. And if you have a non-user, it's 2.4 and 5 volts per meter. There is still exposure, it's not zero. That is the first thing I want to show. So a non-user without other users is still exposed in this situation. But the interesting thing is here the lowest one, a non-user with many other users. If you have an adaptive antenna system, this reduces to about 5 volts per meter. While for the microcell without the massive MIMO, you see almost no reduction. So this shows the potential of these adaptive antenna systems to steer the beam only to the users and not to the non-users. You have potentially places where non-users are less exposed than users. And this is really measured, of course, applied with this duty cycle, but this shows that there is a difference between users and non-users. And I'm finishing. I just wanted to emphasize on this, that this is quite important. So you need to use a user device in the measurements. We compared this with ICNIRP limits, but if you consider also people who don't want to use a mobile phone, don't have a mobile phone, just are not using it, the non-users versus typical versus maximum users will be differently exposed. And what's happening in the future? 4 European projects have been approved, and these projects will certainly look at a new technology. I mentioned it, the millimeter waves above 24 gigahertz, so that's the future. So some tests in the States or networks in the States are already being rolled out, but less in Europe. The new advanced massive MIMO techniques. So this evolves. The first test we did was just in the azimuth that there were beams, then in the elevation, then they become more narrow. So this changes all the time. And then also IEC and CNX standardization is really important, that we do measurements according to these procedures, that we have similar measurements over different countries and can report this to WHO, to IARC, to Anses, to put in perspective with limits and to see whether there is an increase or not with these new technologies. I want to acknowledge also all these people who collaborated and did the main part of the work. Thank you very much for your attention.
Thank you very much, Wout, for this very comprehensive overview of exposure assessment method and recent results. Please Je vais du coup sans transition, vous pourrez poser les questions que
You will be able to ask the questions you wish to ask later on during the Q&A session. After the session, I'm now going to ask Nicolas Noé to come on stage. He's from the Scientific Center for Building Techniques in Nantes. VigiExpo, an autonomous and collaborative system for the characterization of exposure to radio frequency electromagnetic fields. So please, can you tell us about your project in 600 seconds? Well, forgive me for the spelling mistakes. I've seen one here already. I hope there are not many more. So this is a project that's funded by Anses and also XLIM and Geomod. In terms of the context, we have the same context as what was presented earlier on. So some mobile phone antennas, and we pay attention to what's happening for cities and throughout territories. We have some field maps. We're not paying attention to individual exposure in terms of terminal or absorption rate. So this is for local exposure and for what's happening around base stations. We do this as an observer. We abide by local regulations. And when we refer to these type of information, we have several measurements possible or digital modeling. When we make such measurements, well, this has been quite well exposed before, so we can have some dedicated campaigns, we can have sensors in the homes, but we always have limits. That is the location where we place these sensors. If you put them on a vehicle, it can only go through the streets. If you put them in the house, they won't be deteriorated. So you have to make sure where you put it. You can't just put them anywhere. We also have spectral measurements or broadband measures with for frequencies. So this means some cost, and implementation is difficult. You have to set them up, then you have to collect data. So typically what we implement for the modeling of exposure is a beam launch. What we have here, that is on the basis of some digital model of the environment, we're going to determine the spreading patterns and we inject data on diagrams, in terms of diagrams, power, and we are going to be able to map this throughout the city. The problem with these methods is many are difficult to model, and they depend on the quality of data that we have for radioelectric stations. It depends, of course, on when you are. So the idea of this project was to use smartphones as probes instead of normal probes to improve modeling processes. Why use smartphones as probes? Because it permanently communicates with antennas, and especially through the downlink. So we are going to have access to this information through the bars that you can see of the phone. Therefore, you know the power of the antenna and you know the electric field where it is found. And as you can geolocate it, a smartphone is a probe for magnetic fields, electrical fields geolocated. So we have these pieces of information, that is the power of the antenna and the geolocation of the position of the measure. But we have some disadvantages because it's partial information, because it gives you information only on the antenna to which you're connected, which of course depends on the operator whom services you subscribe to, depends also on the frequency band. We also have partial information because, of course, the level of power is modeled through bars on the top of your phone, on the top of the screen of your phone, but the values differ very little. And, of course, you only have strong values, which means that you can never set high level electrical fields. It is not precise because our geolocation, the GPS, is not precise horizontally, only 20 meters, and we don't know about the height the person is at, and we can only work externally. So this is a bit illustrated, but what we were able to see is, well, here you can see on the slide what we had for one antenna compared to the measurement of the spectrum. So where the phone was connected, we could see that what we measured on the phone is exactly the same as the electric field that we have on the phone. So the concept here was about saying, well, our probes are of poor quality, but we have many, which is going to offset this problem. They're not costly and everybody has them, and they're also completely self-sufficient. People are everywhere, and if they go there, it means that they want to know what they are exposed to. If there's nobody, well, there's no point. So the concept developed here through this project was to use digital modeling in order to adapt data that's poorly known on transmitters to correlate what we get on the phones with what we simulate to improve the quality of the forecast.
Évidemment, pour faire ça,
To do this, we carried out validation in controlled environments, in a controlled context. So we have a twofold digital quality approach. So we have to have this to make sure you don't just do this anywhere, and we wanted also to add some smartphone measures, to add two smartphone measures, some precise measurements. If you have people inside their cars, this is going to disrupt transmission. So we had a PC to assess this, and of course walking, so that we have good quality of collected data. The aim was to get back to information that was not known. Here we simulated through some algorithm, a genetic algorithm, which made it possible, depending on the outcome of these measurements, to tune the results for antennas. Here on the left, you have the digital model for simulation in a simplified environment, but still quite telling, quite in line with the real environment. one assessment that we carried out was that we started from an antenna that, compared to publicly available data, is approximately here, whereas actually it is here on this building. But we can see on the phone something that's discretized and simulation in green. So by refining the parameters, we were able to identify the position of the antenna and get to a position that's not far from the real antenna. So the system is replacing systematically the antenna where it really is in the context, in the real-life environment. So by adapting this position of antenna, we realized that we could displace them to have better correspondence, and we see a lot of improvement for areas where the levels are highest. Why? Because there is a masking effect that didn't exist, and if you move the antenna by a dozen of meters, this is very impactful. So here, for a simulation that we got for this antenna, here we have the dB volt per meter, and after optimizing, this is the map we get, and we see a level of error between the simulated level and the real one. Whether you have 0, 1, 0, 2, the difference is not huge. The mistake is of 0.1 volt per meter, but when you are close to the position, it is extremely important, and this is what going to trigger the most significant errors. And to conclude, well, we see that using this type of smartphones, we could improve the quality of simulations, and this would be completely natural. It wouldn't need to modify anything in the modeling of the simulation. If we wanted to develop this on a big scale, we wouldn't need much, because we would use mobile phones. But here we based our work on controlled measurements, and we controlled everything, because it's not really easy to move on to some industrial application. And one important point is that here we are paying attention to optimizing the position of antennas to see that, or to show that it works well. But we don't really care. What we want is, if we modify the antenna with a diagram that's not right, it still be representative of what's happening locally, because you have some masking, or and you can get good results even though the input data are not the same. So this project is using huge database on mobile phones. That's first coverage, so we can get thousands and thousands, and we would be able to use this data to have this type of application. Thank you very much, and I'd like to thank also the people who worked on this project.
Répondre à des questions. Est-ce qu'en salle, vous avez des questions?
Do you have questions in the audience? Well, people are not fighting to ask a question. Yes, there's someone there.
Oui, merci. Dominique Marbouti, donc je suis.
I am the former president of the Radiofrequency committee. You mentioned a potential problem which would corresponded to the weakness of the corresponding locations of the beams. Why not use better resolution beams? Well, when we started this, Galileo was not deployed yet. And so we didn't have Galileo positions. And then we bought phones with Galileo, but the deployment was not good enough yet. But anyway, this question of the location was solved by using a GPS with a precision of about 1 meter. So we have been able to set aside that lack of precision, and that's why we based our work on that hypothesis that the geolocalization would be improved in the future. Do we have any questions online? Questions being read without a microphone? Could CSTB be used as sort of an open bar system? But the data has to be collected. I don't know if with open bar the data is collected. They're here. They could maybe answer the questions themselves, the open bar. But yes, this is typically the type of source. But the more sources of data, the more interesting the situation. What we really need is a lot of data. So the constraint is that we need to have a lot of data coming in. So we have to work with all of the service operators. And a final question from the president, the chairman of the dialogue committee. To go further on that, could this not be a participative science project with the citizens giving their data, and this would get people like you and me involved, people who want to know and who want to participate. This works in a lot of domains. It works for butterfly studies and ionization studies. Could that not be possible? Honestly, in the beginning, that was our idea. We wanted to get people to participate, and we realized that it was a project in and of itself. So we decided to work differently. But that's the goal, yes, because that participative object is of great interest, but we were not able to do it because of the duration of the project. But that is the idea, yes. Thank you very much. I'm going to ask Marloes, and Steph to come up and present the project that we heard about this morning. It's called ACCEDERA, which is a long acronym that has to do with improving the precision of measurements in 5 different countries.
I'm back this time to talk about our project ACCEDERA, which was a 5-country collaboration where we measured microenvironmental electromagnetic field exposure using different devices, as you will see, including a novel body-worn sensor. So, as a bit of background, you've already heard, we do this to be informed about our environment, about the typical levels that we would experience when walking around town in public places, daily life, so to say, rather than any kind of extreme exposure or occupational exposure. What do we experience in daily life is our big question. And of course, this is very important for risk assessment and risk communication. It has also been mentioned already that when carrying a personal measurement device, these have been criticized because of the body shielding. So the idea that your body itself may be shielding some of the electromagnetic fields that is coming from your back, for example, if you're carrying the measurement device in your front, or vice versa. And the other point of criticism has been that these exposimeters are typically calibrated in free space, but obviously they don't float around in free space, so they can go measuring for us, but somebody has to carry them. So they are typically used on body, which is different from how they were calibrated. So Our idea with this project was to design a dedicated and on-body calibrated device to avoid these previously mentioned problems. So this looked something like this. It was our idea to characterize, first of all, using this device, the RF EMF exposure levels in different microenvironments in these 5 countries. Use this novel BWDM, as we called it, which stands for Body-Worn Distributed Exposure Meter, and thereby avoiding the issues with body shielding in real-life conditions. So here you can see how this device was calibrated. This was a setting in an anechoic chamber in Ghent, and this is here on the right. You can see our study assistant who is being calibrated at this moment. So every study assistant who was participating in these measurements had to go through this process before they were able to go out. So this is what that looked like on a typical fieldwork day. Here you can see our study assistant again. Underneath this yellow jacket, he is wearing the BWDM, or as we also have started to call it, the vest, because this is just a little bit shorter. The vest is equipped with 10 different sensors on the front, and those same 10 sensors are also repeated on the back of the jacket, of the vest. In addition to that, in one of the pockets, he's also carrying more off-the-shelf personal monitoring device, the Expom RF, and in another pocket, but on the back this time, he's also carrying an EME SPY 200 device. So, of course, all of these different devices have different frequency bands that they are able to measure. Here you see an overview. All the crosses represent what each of these devices is able to measure. It's not a full match. So when comparing these devices, we looked only at those bands that are actually aligned. So that means they are measured by all devices. I'm sorry if my colors are offset here. But it's mostly the downlink bands and the 900, 800, 900, and 1800 up to 2.6 gigahertz domains. Sorry about that. So the 5 study areas that we that contributed to this project are Belgium, the Netherlands, France, Switzerland, and Spain. And within each of these areas, we took one city, we took one large city, one medium-sized city, and several small villages, just so to represent all different types of environments that people may spend time. And of course, also within these different cities, different microenvironments of public interest. So this is a complete overview of all the different places that we went. I won't go through in very much detail, but what you can see is we had large, medium, and small towns in all of these different countries. The exact towns are listed there on the bottom for all of the different countries. And then we focused on outdoor areas, so downtown, business district, parks, residential areas within these cities, as well as also public indoor places. Here you can think of just shopping malls or universities, railway stations, as well as transportation modes, public transportation modes, so buses, trains, trams, and metros. And this added up to I'll just show you quickly how this was looking in Basel. So we have many different routes here defined. These are all about 1 kilometer routes. It would take our study assistants approximately 15 minutes to walk one of these routes. And yeah, as you can see, we've had quite a number of different places within Basel that we sampled. So in total, this was 357 microenvironments unique that we have measurements for. This amounted to many minutes of data, in total about 33 days worth of measurements. And yeah, 154 measurement days. Our study assistants were aided by this smartphone application that allowed them to keep track of the time and where exactly they were and what kind of microenvironment, so that we could later trace back where they were and when. So this is a time series plot for a typical measurement day, in this case in Belgium, Ghent, if I remember correctly. So here you can really see, like in time, the 3 different devices are listed by red, blue, and green colors. And as you can see, all 3 devices behave relatively similarly. And in the kind of in the pastel colored banners, you can see which microenvironment the study assistant would have been in at that time. So yeah, in general, you can see that these signals look very comparable, both between the VEST, the EXPOM, and the EME SPY. Of course, there's always small differences. And what we did then ultimately is to kind of characterize each type of microenvironment by taking a geometric mean. So here you can see a comparison of those geometric means. You can see that, so in pink we have the comparison between the VEST and the EXPOM, and in blue we have the comparison between the EME SPY and the EXPOM, and what you can see is that they're highly correlated for the total exposure. So that includes the downlink, the uplink, also the DECT and the Wi-Fi. Here, if you can split it out between those different things, you can see that also for the downlink, the correlation is very high. This is kind of what we expected because it's the more stable exposure. For uplink, for DECT, and for Wi-Fi, of course, it's in the lower range because these are mostly measurements from the outside. But here you can also see much more variability. I have to say that in most of this is environmental exposure, so our study assistants had their own phones switched off during these measurements. So that's why also it's not surprising that we see that most of the exposure is due to downlink. Yeah. Okay. So, and we do see that there's actually a slightly lower estimate for the EXPOM and for the EME SPY compared to the VEST. Just to highlight a couple of other findings here as well, we see that the highest exposures, not surprisingly, occur in places where there is a lot of people, so business, shopping areas, and also railway stations where a lot of people congregate. Lowest exposures in residential areas, not, again, very surprising. Also interesting to see was that the busier it is in the tram or in the metro, the higher also the uplink exposure, indicative of people being on their phones. And the larger the town also, the more base station density and the more downlink you will see. So in conclusion, I think we saw that the VEST was measuring comparatively slightly higher levels than other exposimeters, and that these this is comparable with body shielding, compatible with the idea of body shielding. At the same time, it wasn't a huge difference. I would say that still these measurements taken with personal measurement devices, I mean, they reflect at the contrast very well, and they give us a very good idea about exposure in general. The slight downside of this vest type measurements is that the calibration has to happen for every wearer individually, and that makes it almost impossible to apply this kind of a technology for regular environmental measurements, or in case of epidemiological studies or something. This would not be feasible. And we find the same microenvironmental patterns that have already been found in previous studies. So the busier, the higher the exposure, and the larger the town, the higher the downlink. This is already kind of been concluded before. So this work is published in the comparison paper for these three different instruments here. And if you wanted to know more about the design of this new measurement technology, the VEST, this is published here. And with that, I come to the end of this presentation as well. I thank the whole project team, and also to mention it was actually not possible to sit down while wearing this vest. So lots of regards for the people who went out to do all these measurements. Thank you.
Thank you very much. Est-ce qu'on a des questions dans la salle?
Do we have questions in the room for these yellow vest wearers? Is this question related to the subject? My name is René Ducès from INERIS.
You presented the exposure levels. You gave the percentage in parentheses, and I was a little confused because it didn't seem to me the percentage of the volt per meter, but I guess it was the percentage in power.
I'm sorry, can you tell me which? Oh, this is not working
It is a question to Wout.
In my presentation,
Yeah.
there was comparison with equilibrium levels and power. Yeah, I was also confused. So the percentages you saw in this last slide of my presentation were indeed percentages with equilibrium.
Yeah, because if we
power densities for 3.5 gigahertz.
Yeah. If we calculate to the electric field, it doesn't fit.
Yeah.
Okay, thanks.
Yeah, we report in percentage and power levels each time.
On va prendre une question en ligne avant de passer à la dernière.
We're going to take one question from somebody online before we move on to the last presentation.
The exposure for a sensor in clothing statistically different from another one in the same clothing.
I'm sorry, can you repeat that question? I didn't understand.
Over one day, is the exposure for a sensor in clothing statistically different from another one in the same clothing? Between two vests.
Okay, I guess they mean the difference between the sensor that would have been on the front of the vest and the sensor that would have been on the back of the vest.
Or maybe in two vests.
Sorry?
Or maybe in two vests.
There was only ever one vest. There is only one in the whole world. Unless I am misinformed. Whether the coat absorbs any of this, of the radiation, possibly. I'm not aware that it does. These are very, very thin materials, and so I don't think there's any absorption happening there. But coming back to what I assume was the question, yes, you can see difference sometimes between the front of the vest and the back of the vest. Obviously, when you are walking by a base station, at first you'll be facing it with your front, then you'll be facing it with your back. I think the reason that we still found quite comparable results is that over time, statistically speaking, you're going to face away from things approximately half of the time. So yes, if you really zoom in, then yes, you can see these differences. After a while, this averages out.
Okay, thank you very much, Marloes. Please come sit down with us. On va passer à la dernière.
We are going to move on to the last presentation with Joe Wiart, who's going to come up to talk about the characterization of the exposure in residential exposure to RF waves. So first I'd like to thank Anses for having funded my project, for having invited me, for giving me the opportunity to tell you that I no longer work for Orange, and that I may not be white as snow, but in the past I left that operator several years ago, and I've been working in a university, more specifically in an engineering school, which is a government organization. So I'm going to present the results of a project that started in 2016. So the slides are in English so they can be published, but my English is very fair to minion. So presenting this in 10 minutes, a 3-year project which is relatively complex, I've chosen to speak in French in order to speak a little bit more quickly and to remain coherent in my ideas. So this is a project that was carried out between 2016 and 2019, right before the COVID pandemic. It was organized by several institutions. The school that I work for, Telecom Paris, which is a state school, which is part of the Paris Polytechnique Institute, INERIS, which is represented by several people here in the audience today. We had Julien Codeville and Ronnie de Cesse who participated. We also worked with the CNR in Italy, the Université Libre and from Brussels with Philippe Donker, University of Ghent with Sam Hart and others, and Ionke, and another organization representing the Netherlands. The goal of this project was to assess environmental exposure as related to radio telecommunication waves. And it's important to point out here that the assessments that we did in 2016, well, in 2015 when we made the initial proposal, this was the follow-up of a European project that I was lucky enough to direct, and the exposure that we are confronted with is not just exposure coming from the base stations. If we talk about telecommunications, there are telephones on the one hand, and there are relay antennas on the other, and all of these emitters emit coherently. When I move closer to a relay antenna, I receive a little bit more energy from that antenna, but I emit much less to join for my phone to connect with that. So we analyzed and modelized the downlink data from the base stations, and also from some people who are use telephones in the environment, and also the radiation from our own devices. So the telephone doesn't emit the same way when I'm holding up it against my ear as in other situations. With a GSM, the general usage was to have a phone on your ear, because that's the only thing the phone was used for. We only used phones to telephone. And now look at how you use your phone. The usage of a cell phone is very diversified. And with interphone, the population was not 100% coherent. That was not the same as today's usage. Today, I bet that everyone in the room has at least one phone. Some people have some. And if you look at young people, the way that they use their phones, they're not holding them the same as we do. Because people want to see each other. With human evolution, we'll end up with our eyes on the sides of our heads, so that corresponds to where the phone is. So I'm the last speaker today, and I suppose I won't be getting many questions, so I'm going to just relax and talk to you. I'm just talking about engineering. It's just calculations. There's not any... I have no opinion on whether it's dangerous or not dangerous. I'm just talking about calculations. The idea of this study, thus, was to analyze exposure, what's absorbed. Because we're not talking about voltmeters, we're talking about transforming the voltmeters on the sensors into absorbed power, and look at what's emitted by the telephones and translate that into watts per kilo. So we come up with distributions that are different, but the energy used is similar. So we worked with a time analysis. We don't use our telephones 100% of the time. You might have your telephone in your pocket 100% of the time. For a lot of people, this is like a security blanket, and they spend their time looking at the phone. What's going on? What happened in the past 5 minutes? So did I get a message? Has the world collapsed since I looked at my phone last? But the phone only emits when we use it. So emission depends on use. For example, when I go online to see how bad things are going in the world, it doesn't cost energy to my cell phone. I'm not emitting. It costs energy from the servers that are emitting data. And this is what's going to change with 5G. But with all the previous generations, we had a sort of downlink emission, which depended on our location and the distance between ourselves and the base station. With cell phones, it's different. Where is it? What's it doing? How are you holding it? So the spatial, temporal aspect is much more complicated than in an epidemiological study. So we don't measure things everywhere and all the time. Nicolas explained that earlier. We measure bits and pieces. and we try to use the measurements that we've made to try to draw information from those measurements. So we use different techniques. Anyway, I might not have much time left, but I have a list. I have a list of publications at the end of my presentation where you can get all the information. So we're going to aggregate all of the information here. I know that Anses is transparent, and I know that they're going to, I can count on them to share all this. So we're going to measure data between Brussels and Paris, and we're going to look at the geostatistical data. We're going to do indoor analysis. This is more complicated because the only thing we can look at is statistical analysis. And we're looking at statistics and the laws of statistics to find an easier way of measuring this.
We also carried out temporal analysis of the downlink, and the analysis that we carried out is work that we did together with the EST with Sam, and these are surveys that we go on, research that we go on working on as we have sensors set up in France and Belgium and Greece in Santander. French is more convenient to use, I'm sure. Well, the stake here was about having these data merge. I'm going to take one additional minute. After me is just over. No, there is a round table after you. Well, come on. So we merge data. It's the INERIS that work towards this integration of very varied data. This is the result you will get at the end. There's a list of publications, but it's also important to say that these researches gave us the elements to have combined data. These are results that were published, that were already presented to the committee for dialogue. So a lot of this was made public, but these works, same as in many such researches, gave birth to two projects, not four, two, and I'm only part of two of them, Goliath and Sea-Wave, which are going to analyze the exposure, monitor exposure in relation to the use of technologies, telecommunication technologies. So we're going to use, the small difference is that we're going to use in artificial intelligence to see how artificial intelligence can replace tools that were just interconnected. That's it, really. And here is for the list of readings you can make. Well, thank you very much. I suggest that we move on directly to the general discussion on the session.
Posez vos questions concernant...
Well, ask your questions on exposure, modalities, methods.
Alors, si j'ai bien entendu tout ce qu'on a entendu depuis ce matin...
Well, if I understood clearly what we've heard since this morning, this is about, move on, there's nothing to see. So I'd like to know why in France we have people who work in companies and have to abide by some rules in terms of the use of their mobile phones. For instance, in the Paris area, we had 9 people who worked in the same place had glioma, and this didn't trigger any reaction whatsoever. Of course, action was taken, and there is a group on occupational health was set up, saying that 3 people got a glioma following being subjected, to magnetic fields. I don't know whether the speakers are going to be able to answer this question specifically, because it is a question to all the speakers of the day. Maybe it is a point that we can raise during the meeting of the round table, with this question of how one should take into account signals at individual level compared to what to the contribution of epidemiology. Well, I'm completely in line with what you said. When you have a given place, a company or a geographical area with cases that raise issues, the first thing that is going to be problematic is the assessment of exposure. Because you have to see whether people were actually exposed to what you think they were exposed, because you have an a priori about this. So you have to objectivize the physical agent related to electromagnetic waves, and then you can go on discussing independently from the limits, whether you're above or below them. Once you have some level of certainty, you can set up some strategy or discuss with GPs, doctors, and analyze. But if you don't have this element, it remains extremely difficult. But I understand very clearly your question. The first thing is to have documented elements to assess exposure. At the bottom of the room. Good afternoon. Can you introduce yourself, please? Yes, of course. Jean-Pierre Quémont. I'm an inhabitant of the 13th district of Paris, and it is through an association that I found out about this symposium. I would like to say that in the framework of this association in the 13th district of Paris, we carried out an experiment, and I would like to know whether participants found back some modeling opportunity. So what we did with hypersensitive people to electromagnetic fields, we had a route with a smartphone, with a GSM simple device, and the multi-band, I don't remember how you call that, but you defined it because you're the professionals, and we went around the district. And my question is, how do you interpret, how do you model this type of thing? And we could see the differences in the use, in the usage. That is, with a GSM, with the device we had, it triggers radio frequencies when it rings, but then when the conversation is on, there's not much. And the peaks that we noticed, that is, we went above regulatory values of volts per meter, something like that. We saw some peaks for some users. That is, each time you switch on and switch off a smartphone, it is actually striking. Second, Google Map. If you get connected to Google Map, it's also quite striking. two kids playing in a square, in a park, but in front of a radio repeater, an antenna, with the uplink and the downlink. You don't have much. The values are quite acceptable. They seemed acceptable to our participants. And the lowest values is just behind a big wall of cement. That's where we found 1 square meter of a white spot. Some would say electro-smog, but I speak French, so I'd say electromagnetic pollution. That's what we did to actually raise awareness for the inhabitants of the area. Did you do this? Did you materialize this type of experience, and how do you model it? Well, it's not easy. So your probe is a broadband probe, so you measure everything, not only mobile phone networks. And I'm not specialized, but the indicating value is such that you cannot assess the power produced by such a device. But there's nothing abnormal here compared to what we heard, for instance. These spatial variations, these time variations, but yes, we could repeat this, but what for? What are you trying to find out? Is it just to explain how the environment works? Please use a mic. Please use a mic. Mic, please.
Abeille, dans son titre exact.
Sobriété.
Well, you're speaking of sobriety. And I think we're not sober at all. But this is the discussion you're having here between professionals. We carried out this experience just to show that it existed. People don't believe that electromagnetic pollution exists. But yes, it exists. Yes, of course. That's why when you have a pacemaker or another device inside your body, you are told to actually keep it away from your device. So it has some interaction with your device. But if I have such a device, I can go and swim because under the water it's protected by my skin. But of course, when you switch on your phone, it is connecting to the rest of the network, and during the first seconds it's going to try and see which level it can work at. Let's say you have a phone, and if the signal is strong, it's coming down and down. For current technologies, it's not the same. You plug in and you have a certain network of repeaters. For a long time, we were told not to make phone calls when in cars because the level was highest. It was interpreted as if there was a Faraday effect, but it's not at all the case. You're not at all in a Faraday cage. You move from one station to another, and the level is tuned. And this is not at all relevant now with 4G. So indeed, there is a need for explanations. I think that your approach is very interesting. You measure, you check, it triggers things that might be due to electric fields or magnetic fields. I think it's very interesting. And if you accept that Telecom Paris take part, because that can be debated. Sorry, I always get back to this, but I have to say that each and everyone has their hobby. Things need to be explained so that people understand what is happening. Well, I'm ready to stay until 8 o'clock in the evening, but maybe it's not the case for everybody. So I suggest we take one online question before we close this session. So one question to Mr. Noe. Does your study take into account the interaction of 5G with a beam? No, because the research started before 5G appeared, and it's very interesting because, of course, it modifies everything. So we will do things differently next time. Yes, okay, go on. Well, I'm sorry, but this is quite moving to me. I'm going to speak about my colleagues who died. You spoke of being unbiased. Yes, one can be unbiased. I have 3 colleagues in the same office who died. They were just sitting in front of the computing center of Free. I have one colleague who was doing maintenance and spent a lot of time using his mobile phone. He had a tumor on the right-hand side, and the one who was left-handed had a tumor on the left side of his body. So I've been following research on these issues, and there's one thing that I can't seem to understand. The French standards are paying attention to immediate impact and not long-term impact, and I'd like to know why it's so. And also, when we look at all the presentations that were made today, you're not speaking of long-term impact. Why is it? Well, to answer quickly, let me take the floor on this. There was the session on cancer, so that's long-term impact. The impact onto the brain might seem short-term, but it's not the case. We've seen also the intervention of the WHO, and we look at the whole range of impacts, long-term and short-term. And also, your intervention shows that we have to take into account all that I mentioned earlier on, all these signals, individual ones, when we don't understand clearly the link between the exposure of these people, the place where they were exposed, and the impact onto them. So the great difficulty is to get back to the source of exposure, that is the history of people. And we can see in the field of epidemiology how difficult this can be. I'd like to thank once again all those who took the floor, and I'm going now to give the floor to Matthew for the rest of the schedule.